we want to look at now the central limit theorem, but applied to the sampling distribution of proportions. Now, the distribution, again, the shape of the sample proportion, p hat, depends on the sample size n and the value of p. So it is dependent on these two values right here. If n sample size and the value p, population proportion, are just right, then the distribution of the sampling distribution of the proportions p hat can be approximately modeled for probability purposes by the normal distribution. And this is the central limit theorem for proportions. And again, remember the central limit theorem applied to averages and sums, and the sample proportion we already noted is just a average. And when you add the successes, that's a sum. So the central limit theorem does apply to them. So again, we noted that the sample proportion, p hat, is an average of zeros and ones. It summarizes the data as an average. So for the sample proportion, how large must the sample size be? Okay, so again, we said that p and n have to be just right. It turns out that the closer p is to 0.5, the better. The closer it gets to 0 or 1, the worse. Now, the sample size can overcome that, depending on where p is located. So how big does the sample size need to be? And so notice what I said, p and 0.5 is the best, going to 0 or 1 is worse, and n does help with that. So the criteria used will incorporate both of these. N times p must be greater than or equal to 10, and n times 1 minus p, again, must be greater than or equal to 10. If the criteria are not met, we use a different distribution that we're not going to look at this course, the binomial distribution, which is the correct distribution for proportions. So remember, the central limit theorem is just an approximation. It's not exact, but it helps us because we don't have to deal with the actual distribution. Now, one more thing to interpret. Remember, n times 1 minus p, what is this number? This is the expected number. Notice a key word here is number, not proportion, number of failures. And what is n times p? It equals the expected number, again, not proportion, but number of successes. In other words, this number is a sum, the expected number of successes, which is a sum, and this is also a sum of the expected number of failures. So when we did this prior, we were adding the ones. That would be the actual sum we got, but there's an expected sum, the sum that we expect to get, and there's a bunch of zeros, which is the failures we got when we add them up, but we also have a sum or expected sum of failures. But these are just statistics. Right. Suppose that you want to determine the chance that out of 100 throws of a fair 6-sided die, that 12 or less of the throws result in a 4 appearing. Can I use a normal approximation to calculate this? Can I use the central limit theorem? What is it I have? Okay. I have a fair 6-sided die. What am I doing? I need to determine before I can move further what is it that I'm doing. That 12 or less, okay, that's just n. In other words, n is 100. Sorry, n is 100, and this is the count, a number, like the one I mentioned earlier. The 12 or less of the throws result in a 4 appearing. Result in a 4 appearing, so this is success. Can I use a normal approximation? I need to use this formula. So now I have to apply it to the situation. N is 100, but what is P? Well, I need to understand what is it that I'm calling success. A 4 appearing is success. So now the question is, what's the chance a single value, if I toss a die once, what's the chance that a 4 appears? And the answer is 1/6 as it appears. Again, it's just a spare 6-sided die. So again, remember, this value is the probability of witnessing success once in one observation. That's what that number is. So now I'm going to do 100 times 1/6, and it's that bigger than 10. And the answer is, yeah, it is, what is it, 16? 16.66, 66666, whatever. And then, of course, because I have 100, the rest of these, there were only about 16.66. Again, notice it doesn't, the expected value doesn't have to be, you cannot get 16.66, but the expected value is an average also of numbers. So you don't have to be, it doesn't have to be a number that I can actually get when I observe. And so the rest of them must be failures. So when I do 100 times, the chance of failing is 5. 6, is that greater than 10? And the answer is yes, because the rest of these have to be failures. So if I round this, it'd be 17, that would give me 83. So in reality, it's 83.3333 and so on. So clearly bigger than 10. So yes, you can use a normal approximation, meaning the normal model, to approximate the probability. And again, what I'm doing is the CLT, the central limit theorem. That's what I'm saying. My sample size is big enough. And notice my sample size has to overcome the chance of success. Okay, what about this last rule here, the 10% rule? Another important part, when we have sample without replacement, that is the object that we randomly select to measure is not returned to the population. That's what I mean without replacement. So when I do a poll, for example, I don't sample the same person twice. So again, if measures not returned to the population and can never be selected again, then we are altering the makeup of the population and thus changing the proportions within the population. The techniques used in the questions posed here require that we sample with replacement, meaning we need to put that person back in the population but potentially sample them again. This is not done in practice, and it is recognized that if the sample gathered is small relative to the population, we can continue to sample without replacement. Okay, so even though we want to sample with replacement, we can continue doing it without, as long as my sample size is small relative to the population. So what I'm thinking of is this: I have a bag, 20 marbles on black, and the rest are some other color. And let's say there's 100 marbles in there. What's the chance that it comes out black? Well, there's, what did I say, 20? Well, there's 20 out of 100. So that's a chance of my selecting the first one. But, and this is a notation that we haven't covered, but let's say the first one is black. What's the chance the second one is black? Without replacement, this means that if the first one was black, then there's 19 marbles out of 99. So notice immediately the probability of selecting black has changed. And what if it had been the other way around? Not black, then the probability would have been 20 out of 99. Okay, so without replacement means that once I select the first one, if my population is finite, then I'm altering, every time I sample, I'm altering things. I'm altering the probabilities, and that's something that's not to be done for these calculations. However, if my sample size is small relative to the population size, then these numbers are not going to change by much, and we are going to be fine. Okay. What is the rule? How big is the sample? As long as the sample is not bigger than 10% of the population size, we can continue as if nothing is wrong. Now, in question 4, the 6-sided die, are we sampling with or without replacement? Well, let's see, with or without replacement. Every time I toss a die, what happens? Well, I get a value, and then when I pick it up, does that value go away? No, it can roll again. So even though I am not taking anything out or putting any, taking out or putting it back, the die result from sampling results in sampling with replacement. So it's the equivalent of this. So we are sampling with, again, replacement. A quick example, what if my population size is 1,000? How big can the sample be? For what? To say that I'm sampling with replacement. And the answer is take 10% rule. So just take percent of my population size. And this is max size for sample. So as long as my sample size is no bigger than 100, I can pretend I'm sampling with replacement. I can pretend. Obviously, I'm not, but I can pretend like I'm sampling with replacement. Otherwise, then I have to do something like this. There's other formulas that deal with sampling without replacement.